My name is Thijs Heijligenberg. I'm presenting the paper BigMac, Performance Overhead of User Plane Integrity Protection in 5G Networks. And this is joint work with my colleagues from the Radboud University, Böhm University and Reddick Security. So for an overview, so the title without the emoji spells Performance Overhead of User Plane Integrity Protection in 5G Networks. So there's three components here: performance overhead, user plane and integrity protection, all in the context of 5G networks, of course. And I will be introducing these and then going into the results on the performance overhead in the following order. So I'll first introduce user plane, then integrity protection, and then performance overhead. So in 5G or in mobile networks in general, we have some division between the control plane and the user plane. So the control plane would be your messages with the authentication, all the messages that we've seen before in the previous talks. And then the user plane is carrying your IP data, your website requests, your SMSs, etc. Both have some level of confidentiality. For the control plane, you should use it, and for the user plane, it's recommended. What that means is weird. And for the integrity, we now are in the same situation, so we always have had integrity for the control plane. And since 5G, we have integrity protection for user plane traffic. So previously, we didn't have any integrity protection for the user plane traffic, but we do have that now in 5G, but it's optional, same as confidentiality. And optional means that it's mandatory to implement, so your UE has to do it, the network has to support it, but the network is supposed to set the flag like, yes, we are using it for this data radio bearer. And they don't have to. And they don't have to because they didn't want to. In the 3GPP discussions you can read, they don't want the overhead of doing it always. So why do we have user plane integrity protection? Well, one of the reasons is the alter attack in LTE. So this is where you have known plain text, which is vulnerable to the malleability of the encryption because there's XOR and then you can make a mask. It's a complicated stack, but it relies on the fact that there is no integrity protection of the traffic. And even though it's encrypted, you can then mess with it. And this could be solved by higher layers doing integrity protection. In this case, this was not applied, and that was an issue. And that's why one of the reasons why you want integrity protection for your 5G user plane data. So we have free integrity protection algorithms available. They're the same ones as for RRC and NAS. They're called NIA 1, 2, and 3. They're the same as EIA 1, 2, and 3, which are the ones for 4G LTE. They're the exact same. NIA 1 is based on SNOW, NIA 2 is based on AES, and NIA 3 is based on ZUC. You should always, as a UE, implement NIA 1 and 2. NIA 3 is optional. And yeah, SNOW is from the 3G era. The other two are from the 4G era. So after 3G, they cleared it up a bit. And then there's also the weird null cipher NIA 0, which you should not use according to the specifications, which doesn't mean anything. But yeah, these are the ones that we have to play with and that we are looking at for the overhead. So the overhead mentioned or expected to come from these algorithms is, or from the integrity protection is in latency, because the computation of the max for the integrity protection takes some time. Throughput, because they take resources on your CPU. And then there's also some other factors that you can look at, such as battery consumption. We didn't measure those. We couldn't get a reliable measurement in that environment. So, yeah, we looked at latency and throughput for the free algorithms, and we did some benchmark testing of the algorithms on a laptop to see how they compare, etc. But mostly we tested them on a live UE, so commercial phone and a Microsoft call box for the base station and core, testing the latency and throughput. So in practice, we got these results. So this is a normal setup for the Microsoft, except that we changed that we have integrity protection, and then NIA 1, 2, or 3. And we see that there is some influence of the integrity protection here. whether you use NI1, 2, and 3 doesn't seem to matter that much in this case. But there is some overhead. You can see it's up to 5 milliseconds. But the weird thing is that the runtime of these algorithms is way lower than 5 milliseconds, especially for NI1, 2, NI2, and 3. It's below 100 microseconds. And this is also exemplified if we use another setup used by the Amarisoft. So that's a setup for low latency, specifically, which gets way lower latency, impressively low latency, below 10 milliseconds. And there we see that the difference is much smaller. So apparently the Amarisoft can make the difference go as low as 2 to 3 milliseconds, which is then the impact that your user plane integrity protection has on your latency. And then for the throughput, we also measure that with just getting a web server, getting as much traffic as we can. And there is barely any effect from the user plane integrity protection. So we see that there is some slight variation introduced by it, but nothing on average basically influencing it. And in the low latency mode, which of course has lower throughput, it is a trade-off, there's also no difference. So if you do any effects were seen in the latency part. So some remarks about this. So I mentioned already it's an Amarisoft call box and a commercial phone. Both are black box. We don't know how they handle their pipeline and how these latency gets introduced, how they make things go as fast as they do. They are quite complex because the whole system is very complex, and we don't know what parts they optimized. So we don't know how they made the low latency go this low, etc., or how they made, or what implementations they use for the ciphering and integrity protection. And it's also not a full-scale network. But for the optimization part, our paper contains a whole section on possible optimizations that can be done for this setting, which was done by my colleague Christian Böhm. He's also here. If you want to talk about the optimizations, talk to him. Which can make the runtime of the algorithms go much faster in the whole setup. So in conclusion, we have that user plane integrity is not in general a deal breaker. It will give you a tiny latency hit, but no throughput hit, and there are ways to make it faster, for which you should read our paper. And that concludes my talk. So, are there any questions?
Questions?
Did you think about like a BTS side overhead when every UE is with a UPIP, full rate UPIP is enabled? What kind of overhead is expected in the cell towers?
I don't know. We didn't have a cell tower with 100 UEs attached to test with. So, yeah, we could see that the Amarisoft could still reach that throughput and that latency. We didn't stress test the Amarisoft to see like how many UEs can we attach and then does it get better. But apparently for the throughput, it's more bound by the just overall like limits of the physical layer than the user plane integrity protection. But we didn't. That's also why I said it's not a full-scale commercial network. We didn't test that aspect.
More questions? All right. So let's thank the speaker again.